Okay, welcome to note set number 5, where we'll talk about matrices and talk about how to multiply a matrix times a vector. Because remember, that's a big part of our main focus, which was solving AX equal to B, where A is a matrix, X is a vector. So that AX is the matrix times vector part. And I don't know if I mentioned this in the previous note sets or not, but I indicate here underneath the title of the note set what section of the textbook these come from. So you should be doing the reading in the textbook as well as watching the videos and studying the notes, because the textbook does give some additional insights that I don't cover in the notes. Okay, so matrices. Well, we've already seen scalars, we've seen vectors, and so a vector you can think of as stacks of scalars, and you can think of a matrix kind of as a stack of vectors, although we'll stack the column vectors next to each other rather than stacking scalars on top of each other. So matrix just carries the generalization up from scalar as a single number. A vector is just along one dimension, so we have a column of numbers, or less commonly a row of numbers. And then a matrix is a two-dimensional array of numbers. Now, don't get confused with the use of the term dimension here, because we use that to describe the dimension of a vector, is how many elements there. So here we're talking about how many different directions we're filling in a matrix. So here's a picture of a matrix. We use, for notation, we use an uppercase. I prefer non-italic and bold. Now, if you're writing that by hand, you would write an uppercase A and then put a double underscore underneath. That's how we would write that by hand. And just like we had a way of indexing elements of a vector, we have ways of indexing elements of a matrix, except now we need a double subscript. So the subscript is telling us the first entry tells us the row, and the second entry tells us the column. So AMN is in the mth row and the n column. And you can always remember that it's row first and then column. And if you remember Roman Catholic, that'll help you remember which order those are. So this A sub M1 is in the mth row and the first column. So the matrix, as we show it here, since we have 1 down to M in the first position, has M rows, and then we have 1 out to N columns, so we have N columns. And we refer to this as an M by N matrix. So when we see M by N, again, remember Roman Catholic, we have M rows, N columns. And we'll often write things like this. We can say A sub ij, and then tell you the range that I and j can take. So I goes from 1 up to M, and j goes from 1 up to n. So out of the three that we've looked at, the matrix is the most general of the three, but obviously contains the others as a special case. So an M by 1 matrix has M rows and 1 column, so it's a column vector. And a 1 by N matrix has 1 row and N columns, and that makes it a row vector. And we can even have a 1 by 1 matrix, which doesn't look like a matrix at all, but technically it is. It has 1 row and 1 column, so that means it's just a single number. It's a scalar. Now, I'd like to just point out in passing that there's something that's even more general than a matrix. So tensor, Tensor, tensor is a generalization of this idea, and that could have rows, columns, and then like sheets you could think of. So that actually that would be a third order tensor. So actually a matrix is a second order tensor, vector is a first order tensor, and a scalar is a zeroth order tensor. So it counts the number of directions that you're filling in. So you could think of a tensor, here's a matrix, and then if we think about going back in this direction, let's see how well I can draw with my mouse. Not bad, actually. So we would fill in elements here to make the matrix, and then we would have another sheet behind that, and another sheet behind that, and another sheet behind that, and so on, however many there are. So we could have M in this dimension, we could have N in this dimension, and maybe Mn. I should have done L. Well, let's just do L. We'll do L in that dimension. So that would be an M by N by L tensor. So that's a third order tensor. And you could have a fourth order tensor. Yeah, it's a little hard to think about that. And you could have fifth order, you could have any order. And these things do show up sometimes, but less often than matrices and vectors and scalars. So let me clear that off so that we can read what I've written here. So we won't be dealing with tensors. We'll stop at matrix. But the thing is that as mathematicians developed this idea of matrices, they needed to develop a set of rules for how they worked, as far as like additions and multiplications and all that would allow them to do useful things with them and describe, use them to describe the physical world as well as mathematical concepts. But they needed, since this was a generalization of the idea of vector, which is a generalization of just a regular number, they needed to make sure that these rules, as they were developed, were consistent with the old ideas, so that when you collapse down to the scalar case, the rules still work. But what they also discovered was that when new ideas arose, those didn't necessarily have to be consistent with, there could be characteristics of a matrix that went beyond what you would have for numbers, and we'll see some of those in just a little bit. So as we're studying AX is equal to B, and remember A is a known matrix, B is a known vector, and X is an unknown vector that we're trying to find given A and B. What we're showing here on the left side is matrix multiplication of A, so a matrix A multiplied by a column. And so we need to take a look at this matrix vector multiplication. So a matrix times a vector, and unless we say otherwise, when we say vector, we mean column. So we can't even do a matrix times a vector multiplication unless the dimensions of the matrix and the vector match properly. So not every matrix can multiply every vector. So let's say that we've got some matrix A, and we'll just include as a subscript here M by N so that we can keep track of what its dimensions are. We don't always do that, but it's helpful when we're trying to explain the requirements for dimensions. So we'll say that that's an M by N matrix, and let X be an N by 1 vector. So as we said, it's a column vector. And then for that case, we can form the product of A times x. And the reason that we can is because when we look at one thing times another thing, and it doesn't matter whether they're matrices or vectors, as we'll see, when we take matrix times matrix, vector times vector, since a vector is also a special case of a matrix, once we've defined matrix multiplication, that handles any case where we have matrix times vector, vector times vector, vector times matrix. They all must satisfy this rule. So the inside dimensions must match to allow this multiplication. So in this case, we've set it up so it's m by n times an n by 1. And then the other cool thing about this, a little way to remember this, is that what do we get from this multiplication? Well, when we multiply this, as long as the inside dimensions match, the result will be a general matrix or vector whose dimensions are given by the outside dimensions. So in this case, the result of this m by n matrix A times an n by 1 vector will give us, we look at the outside ones, m and 1, so we'll get an m by 1 vector. So you can always puzzle out what the size is going to be, and you can always puzzle out if the sizes are correct for allowing the multiplication. So to see what this actually does, so if I gave you an m by n matrix and I gave you an n by 1 vector, what does it mean for that product? So that's what we'll take a look at next. And we'll look at 4 different ways of visualizing this. It's not that it works 4 different ways. No, all 4 of these ways give you the same answer. It's just that sometimes it's easier to think about it one way than another. And it depends on what it is that you're trying to accomplish. What question are you trying to answer, or what insight are you searching for? And often we need to be kind of simultaneously thinking about 2 or 3 or maybe all 4 of these ways all at the same time, because they might be giving us slightly different angles on insight for how this works. So the easiest way to just talk about this, what I call quote-unquote by hand computations. So what you would do by hand to just work out the answer. You're not looking for insight, you just want an answer. And sometimes that's what you need, but sometimes you need more, and that's what the other views are for. So we just simply say that I've made this set of numbers very easy to keep track of: 1, 2, 3, 4, 5, 6, and we see that we take 1 times 5 plus 2 times 6 gives us the 17, and then 3 times 5 plus 4 times 6 gives us the 39. So it might not be clear what the machinery is and how you would do that in a more general case, but let's take a look at another one, and maybe you'll see the pattern here. So now I've got 1, 2, 3, 4, 5, 6. I've got 7, 8. Well, we should have checked to make sure our dimensions work. So we've got a 2 by 2 and we've got a 2 by 1. So the inside dimensions work, so we can multiply. And the result is going to be the outside, so it's a 2 by 1, and that's actually what we got. So you need to get to the point where you can just look at something laid out like this, and you'll know instantly, A, it works, and B, what dimension you get. It's extremely important to be able to do that. Here we've got a 3 by 2, 3 rows, 2 columns, and we've got a 2 by 1. So those will work together, and we know that we will get a 3 by 1 coming out of that. Okay, so we know that those will work, and again, we see some mysterious 1 times 7, 2 times 8, and so forth. So we kind of need to figure out how that will work. Here's a couple questions for you before we talk about how this actually works. So most of the work that we do will be a matrix times column vector. Can we reverse the order? What do you think? Check the inside dimensions. Does that look like it will work? No, it will not work. But I will let you know that you should think about what happens with a row vector times a matrix. So we can never do a column vector times a matrix because the column vector always has a 1 here, and a matrix, a true matrix, will always have something other than 1 there. So we can never do column times a matrix. But you should be able to convince yourself that at least sometimes, with the right choice of row vector and matrix, that you can sometimes do this. So if we go back up, let me just see. So I'm going to, on the next page, I'm going to show you, how we get these mysterious combinations. Maybe you can puzzle it out, but here's a simple way to do it. So first, the trick to find whether we've got the right, what size result we're going to get. So the first thing you got to do, like I said, is just check to see can they multiply. So just check the inside dimensions. But then a little trick to find out what size. I mean, you could check the outside dimensions, but this is a nice visual thing. Let's look at this example. We're just going to take the vector and move it up so that we now kind of have this grid where there's nothing up here, but we put the right hand side one up here, and we put whatever is on the left hand side multiplying over there. And if we now draw placeholders that match up with the dimensions, so we've got 3 here and we've got 1 here, so that's the size that we'll have. So that's the trick for finding the right size, and this will work for any allowable pair that will multiply. So it doesn't matter if it's matrix times vector, matrix times matrix, row vector times column vector times row vector. All of those, you can first check that they can be multiplied, and once you're past that hurdle, just do this little trick to see how the things get filled in. So, we've worked this example out up above, so we know that what goes in this position is going to be 23, and what goes in here will be 53, and in the last entry we'll have 83. So that's how to find the right size. And now there's a trick to get the numbers right. So here's that same example. And so what we're going to do is, after we've shifted it up, so let me back up here to the previous page. So we've shifted this up, and then we're just going to rotate this down so that the numbers match up. So and that will always work because that's the check for inside dimensions. So the number of elements down here has to be equal to the number of elements along there. So that's the number of columns on the left have to be equal to the number of rows. So when we fold it over or rotate it over, you get something that looks like this. So now we've kind of aligned it there, and so that's the trick. And then what we do is, so we rotate the vector counterclockwise, align it with the elements in a row of the matrix, and then we form the product of each lined up pair. So I've circled in blue the lined up pair. So 1 and 7 line up, so we form the product of each lined up pair, so 1 times 7, and then 2 times 8, and then we add the products and place the result in the new vector. So 1 plus 7, or 1 times 7 plus 2 times 8 gives us 23, and that goes in there. And we do the above for each row. So there's the doing it for the next row. We imagine moving the 7, 8, the rotated 7, 8 down, lining up with 3 and 4. So we get 3 times 7 plus 4 times 8 gives us 53. And then the last one, 7 times 5 plus 6 times 8 gives us 83 there. So what you need to do is practice doing this so that you can do it without thinking. This is not something that you want to have to sit and think about. So you need to practice until it's second nature and you can just do it. And in fact, for simple cases like this, you can kind of just do it in your head. All right, so this next view. So this is a completely equivalent view, and this is what I call the formal math rule. So this is how the mathematicians write it out. And unless you are good at reading math notation, it's maybe a little hard to follow what this means. But this is really just writing out what we just did. So so you can see here, if I choose, I'm allowed to choose I from 1 to m. So all that's doing is choosing successively each of the elements in this result column. So if I want to know B1, I'm going to let I be equal to 1. If I want to know B2, I'm going to let I be equal to 2. So let's take a look at what happens with B2. So I put B sub 2 there. That I'm still going to sum from j equal 1 to n. But what's going to happen here? I'm going to get I set to 2. So it's going to be A2j times xj. Well, what is that saying? So here's all the A elements that have 2 in that first position of the subscript. That's what it's saying. So take this for j equal to 1. So that would be A21 times x1 plus, that's what the summation is telling us to do, plus, now we're jumping up to j equal to 2, A22 times x2 plus A23 times x3, and so on, all the way out to A2n times xn. Well, isn't that exactly the same as taking this vector, rotating it, and lining it up here? We would have the x1 here, we'd have the x2 here, all the way out to the xn here, and then we would be forming those little products just like we did, and so on, all the way out to the end, adding all those up and writing it right here. Well, that's what this equation says to do, and here's the one for B3, and so on. So, so this is really just writing out in math notation this rotate, align, multiply, add trick. That's all there is to this, really. Now, we're not going to use this formula very much, if at all, really. We'll be more likely to use the by hand rule or one of the two rules that are coming up. But if you were taking this in a math department, this would be a workhorse, because you'd be proving things like, what happens if you do a matrix multiplication, matrix times a vector, and you transpose the whole thing. We haven't talked about transpose yet, but and then you do something else to that product. What's the result? And we need to prove that. Well, our proof would use this formal math rule definition, but we're not going to focus too much on this. But you need to have seen this. Okay. This is the big one right here. Matrix vector multiplication as a linear combination. And this is how we think about matrix vector multiplication. So the by hand rule is how we ourselves actually do this multiplication. But this is how we think about it, so that we can understand, why does it work that way? Or is it possible to get this result? Or why is it not possible to get such and such result? Just knowing how to do the multiplication with numbers is not enough for you to really understand that. And yeah, let me just say this, right now. I know that a lot of students learn best by just doing lots of examples with specific numbers in place. And yeah, that's a great way to learn how to do this. But you do need to move beyond needing numbers to be able to understand what's going on. Because as engineers, we often don't have the numbers until the very end. We're often formulating things in terms of arbitrary variables that our job is to figure out what those variables need to be. So if you can only work these things out when numbers are already plugged in, you're not going to be able to do real engineering work, because real engineering work is often figuring out what numbers need to be used. And you need the arbitrary symbols to play around with and stand in for the numbers that you haven't yet put in there yet. So I'm illustrating these with numbers, but you need to be able to think through these things with just arbitrary symbols as well. So practice these things with numbers, but then practice them with symbols as well. And practice, really, you got to do the work. This stuff is not easy. It doesn't just come instantly. And you're only going to grasp it if you work at it. So anyway, enough lecturing. Let me move on with the view here. So we've already seen this. This is the same example. But now I'm saying we should view this as a linear combination of the columns. So we see that we've got the first column of the matrix sitting right here, and the second column of the matrix sitting right here. And what are we doing? We're taking this 5 here and putting it out in front of that first column, and we're taking the 6 here and putting that out in front. So this is a linear combination of the two columns, where the weights come from the vector that we're multiplying here. And so we get, in this case, just like before, 17 and 39. And you can figure that out. You get 5 and 15, and then you get 12 and 24. And so if you add 5 and 12, you get 17. And if you add 15 and 24, you get 39. So everything still works. So you got to believe me. So let me clear off some of this ink here. So I just put a blue rectangle around the first column and show. So here's our by hand view that we just did. So I'm identifying where that column is, and I can create this action of 1 times 5 and 3 times 5 by pulling the 5 out in front of that column. And then we have the 2 and the 4, which shows up there, and the 6 works together with that. So we can see that this does actually work. Like I said, it's less common that we actually do it this way, although sometimes we will. But this is a great way to view what this matrix times vector is actually doing. So get burned into your brain that matrix times vector is really just forming a linear combination of the columns of the matrix, where the weights that are taking part in this linear combination come from the vector that's being multiplied. So remember that our job here is to solve the equation AX equals B. And remember, we'll know A and we'll know B. And so let me put a double bar underneath that and a single bar underneath that. So when we're trying to think about this problem and ask, is there even a solution to this equation? Because that's a question that we should always ask. We can write down an equation, but there may not actually be a solution to it, right? I mean, you could write a second order polynomial on the left equals 0. There may not be any real roots, right? And so, back in the day before they invented complex numbers, people said there were no roots of certain polynomials. And so it may be possible that there is no solution to the equation. Or it may have solution only under certain conditions. And it's this view, not to do the work, but to visualize what the work is and whether the work can even be done. So that will help us realize that there will be a solution only if B, the B vector, I should not, oh crap. Well, only if the B vector can be written as a linear combination of the columns of A. If B cannot be built from the columns of A, then there is no solution to this equation. And we'll talk about that more. So this is another way of visualizing this. So we've got this matrix A. So on the right, here's our matrix A. That's this thing here. And so what we're doing is we're showing each one of these as a column. So each one of these is a vector, lowercase bold, and non-italic as I like it. So each one of those is a column. So we're visualizing our matrix A as being a side-by-side stacking of columns, and we think about folding this over. Well, x1 is going to multiply every element in A1. That's why we get this. x2 is going to act upon all the numbers in this column. And so that's why we get this. All the way down to xm will be acting on all the numbers in this column. And that's why we get this. So here's our linear combination. So the only thing that A times x can be equal to, there's only certain things that we can put over on the right-hand side. They must be something that can be built from a linear combination of the columns. And so we'll soon see that this all ties in with the idea of linear independence and things like that. So this is a super important idea. This is our visual ticket to how all of this linear algebra works. Now, a third way of visualizing this is with inner products. So here's our same example. And this one does show up as being important sometimes. Again, more of an insight perspective than a computational perspective. But it shows up, but it's not quite as important as the linear combination view. So here's our example. And let's look at what we do to compute the number 17. Well, we do 1 times 5 plus 2 times 6. And we suddenly realize, gee, that looks like an inner product. If you remember when we did an inner product between two vectors, we took their first two elements and multiplied them, and their second two elements and multiplied them. In fact, we multiply every pairing of elements and then add them all up. Well, remember when we fold this thing over, remember we were pairing 5 with 1 and 6 with 2. And then we added up those products. So really we can envision 1 and 2 forming a column vector and doing an inner product between that column vector and the vector that we're multiplying. And that gives us 17. And then likewise, we can do the same thing with the other one. Let me clear off this ink here. So to get the first element of our result, we do an inner product between the first row of the matrix and the vector x that we're multiplying, and that will give us the first element. Then to get the second element, we take the second row of the matrix. So we would take this inner product with the same thing. So now we get 3 times 5 plus 4 times 6. So this idea that the ith element of the resulting vector is nothing more than taking the inner product between the vector x that we're multiplying and the ith row of A, but just envisioning that ith row turned so that it becomes a column. And that's the idea. So this is a good way to sometimes visualize this. So here's our 4 ways that we've had to visualize this. So the first one is the rotate, align, multiply, add trick. That's nothing more than the trick for the by hand. Then we had the formal math definition. So that wrote it out in terms of a sum with all sorts of subscripts, i's and j's, and so forth. And the place where that's used is for proving theorems, and we're not going to really do that in this course. But if you were to take linear algebra in a math department, their job is to learn how to prove all the theorems and to train you as a mathematician would be trained. So they go through all the proofs, but we're not going to do that. Then inner product between vector x and rows of A. So hint, hint, hint. I didn't put these in the same order that I introduced them. So number 3 here is the last one that I introduced. So this is comes in handy sometimes. And then last and certainly not least, in fact, the most important, our most very powerful way of doing this, at least visualizing it, is a linear combination of matrix columns. And so that ends this set of notes. So in this set of notes, we introduced what a matrix is, and we talked about matrix times vector. Now, all these rules can be expanded to matrix times matrix, or certain combinations of vector times vector, and we'll run into those later. But remember, the most important thing for us is thinking about the AX equal to B. So matrix times vector is the most important. All right, so we're at the end here, and I'll see you in the next set of notes.